Good morning, everyone. Welcome to the lecture of the material science. As usual, let's recall what we have learned in the last lecture. This is the summary of the material we learned last lecture, and we started to know that how to address the crystallographic points in a unique cell, and also we want to know the crystal actions in a like this in the unit cell, and this is square bracket, right? Square bracket represent direction, and caret bracket means what? Means the family, right? Family. Okay, I hope you remember family of the direction of the family of the direction. Okay, and then the plan here we call it crystallographic, and we use parentheses to represent the crystallographic plans. Again, this is breast bracket. Breast bracket means the family of the plant, right? Okay, so I hope you remember. And this also have a special name called Miller index. Miller index. Right. So these three topics are very important, especially the last two, direction and plan. So I want you to remember this very well, and we will have this in your final exam. The fourth one is we need to know the direction will be perpendicular the plan. For example, 100 direction will be perpendicular to the 111 plan. Okay, so this is direction and plan. It will be perpendicular. Okay, I hope you still remember this. Very important. And the fifth point is crystallographic cubic crystal and hexagonal crystal. You need to know how to convert these three numbers to four numbers. Convert from four numbers to three numbers. We have equation for you to do this, so please remember. And next one will be atomic arrangement. Atomic arrangement means that you need to find a repeat unit in two dimensions. Two dimensions. Okay, and then next one is interplanar spacing. For example, this is 111, right? This is 111 plan, and this is also 111 plan. So what's the distance between these two plans? We have an equation here for you. For example, this is 111, right? And then that will be D111. So A is what? A is the edge length. Divided by what? Root h power 2 plus k power plus l power 2. HKL represent 111 represent 111 here. So you need to do the calculation for the interplanar spacing using this equation. Again, I want you to remember this equation so you can do a calculation very, very quick. Okay, and then later on, we introduce linear density and the planar density. And especially, we want to know the linear density and planar density because it is important related to the properties of the material. For example, if you have a higher planar density on the surface of your material, then if we regard each atom is act as a catalyst, so you will have a lot of catalysts on the surface. That means you will have faster reaction, or you can have faster reaction and more reactions on the surface. So we use catalysts for you to understand the planar density. And also, this is in terms of the chemical properties. In terms of mechanical property, for the slip, if you have a higher planar density between the planes, then this is the plane which is easy to slip, right? So this is in terms of mechanical properties. Okay, so please remember all this information you want to digest, and it's also important for you to know and in your final exam. Okay, so today we move to next section in chapter 3. We want to start to introduce single crystal and polycrystalline materials. Polycrystalline. And also later on, we will introduce you anisotropic, X-ray diffraction, and the non-crystalline storage. First of all, let's move to the section 3.13, single crystals. So why single crystal? I'm sure you know now very well is this. Look, this is single crystal, and we learned amorphous in the previous, right? Amorphous means these atoms doesn't pack in there, but some of the crystal which is very small, and there are many small crystals packed together, and this is what we call polycrystal. Okay, this is what we call polycrystal. But first of all, let's take a look of the single crystal first. So single crystal is what? We learned this already. The periodic and the repeated arrangements of the atoms is perfect or extends throughout the entirety of the specimen without interruption. Okay, this is the definition. So you have many repeat units, right? In 3-dimensional or in 2-dimensional. Okay, this is the single crystal. It exists in the nature, or you can produce it artificially. So you can make single crystal. For example, this is what we call silicon ingot. Silicon ingot is for to make what? Silicon wafer. And silicon wafer is for what? Is for us to make semiconductor chips. So this is artificial made. But you can find this single crystal in nature. For example, diamond, right? The beautiful diamond. Diamond is very good, very expensive, beautiful. Okay, so single crystal has become extremely important in many of modern technologies. This is one of the example I just show you. Electronic circuits. Okay, this use single wafer. So there are many single wafers used, like solar cell. You use silicon wafer, again, right? Or LED, you use aluminum nitride wafers to make LED, for example. So there are some example here for you to know that diamond, okay, and calcium fluoride, this kind of things, and the jewelry, many single crystals. So instead of beauty or expensive, what is single crystal for? This is some of the example for you to know that. So some engineering application require single. This is a single crystal diamond, very small. You know, you can make artificial diamond, but it's not perfect, but it's good enough to do the what? Abrasive. Okay, you can do this. You can polish things very well. Okay, so this is diamonds for. And you know the turbine brands. The turbine brand single crystal. You know, if your engine has a turbine in the engine, so you don't allow any mistakes in the engine, in the turbine, right? So especially turbine brands need to be single crystal. If you have a polycrystal or disinfection inside, and you will have trouble when you get on the plant, the engine has problem, right? You don't want this to happen. Okay, right. So these are some examples for you to know that crystals as a building blocks. Next is the polycrystalline materials. This is how it looks like, the polycrystalline. As you can see, this part looks right. If you take a look closely in the atomic point of view, and you can see that this area, the atom packed well, but an area atom packed well, but between two single crystals, there's a gap. or there is a boundaries between single small crystals. And this is how it looks like under the SEM observation. You there's a this we call boundaries, grams, and gram. This is a gram, single crystal, gram. Okay, as you know, is single crystal polycrystalline. Polycrystalline gram and the gram boundaries. Okay, very easy. So the stages in solidification of the polycrystalline material. How polycrystalline material made? You can imagine you have a solution which is sodium chloride solutions. So if you put a, a teaspoon of salt into this into the water, salt will melt, or salt will dissolve in the water, right? And you put more and more and more and more. And then if it's ultra saturated, the salt will start to what? To get together, and we can make it become a crystal. So this is how it looks like. Stage in solidification of a polycrystalline materials. In the beginning, you have only little bit crystals, small crystals in a solution. Okay, it doesn't need to be in a solution. It can be a melted material or substance. Okay, and you start to decrease the temperature, and you start to this single crystal started to grow. So square grids depicted unit cells, a small crystalline nuclei. Okay, we call this gram. Imagine when you start to reduce the temperature, you will have more crystal get together, and it becomes small gram become bigger gram. Okay, so this is called growth of the new crystalline. Okay, so there are some grams that are adjacent to one another, so they get together, they put it together. I'm sure you have done this when you are in high school. And then if you decrease the temperature more, and you will have some kind of complete of the solidification. So that means what? That means all the grams touch to each other. And this is called what we call gram boundary. And this is what we call gram, right? Hope you still remember. So as a result, you can use this cartoon to represent this polycrystal. So the gram structure appear under the microscope. Dark line are the gram boundaries. This is represent the gram boundaries. Okay, so there are two steps, very easy. The first one, you need to form nuclei, formation of nuclei, very important. The second is that nuclei grow from the crystal. We call the gram structure. Easy. Okay, so normally how you make polycrystalline can be formed like this. Start with the molten material for all the liquids, like metal, for example, like gold, silver. You melt it and start to make it become solid. So you will become polycrystal. Start from this, and then nuclei first, and we have liquid. And then you decrease the temperature, and you have small, from nuclei becomes small gram, right? Small gram. And then from small gram to become bigger gram. So this is called gram structure. Okay, very easy. So this is how it looks like from A to B to C, and then D can represent this. This slide is that the solid are composed of the collection of many small crystals, or we call grams. Such materials are termed polycrystalline. So exists some atomic mismatch with the regions where 2 grams meet. And this area called gram boundaries. So atomic mismatch means that you have growth direction in this direction and you have growth direction in this direction. So they are somewhat. So direction of crystal growth like this. For example, growth direction, this is growth direction. And the direction is mismatched. So you have gram boundary. Yeah. Okay. If you have same direction of growth, then that won't cause polycrystal. That will cause what? Single crystal. So let's think of gram boundaries. What's good about gram boundary, or what's bad about gram boundary? And what's good? What's the difference between the high angle gram boundary and the small angle gram boundaries? You know, high angle gram boundary has more space between 2 grams, right? Small angle gram boundary means that it's more close. You know, this direction, this looks the similar. The direction similarly go to the same direction. So this is called small angle gram boundary. So what's good about this? What's bad about this? So the region between crystals, the transition from the lattice of the one region to that of another. So this is small gram boundary is slightly disordered, right? Compared to the high angle gram boundaries. So the important thing here you need to remember is that compensity of the gram, the density of the gram boundary is what? Low, right? So low density in gram boundary. This has low density. That means what? If you have a low density gram boundaries, you will have high mobility. Atom will move, easy to move, right? So we call mobility. And you will have high diffusivity. So you have foreign atoms. For example, if you have foreign atoms here, for example, this is gold, for example, and you have a carbon atom here. The carbon atom will be easy to move, right? For the diffusivity. Okay, and then you will have what? High chemical reactivity. Why? Because this atom is not bound very well to the neighbor atoms. So there's some kind of bond missing. So if you have bond missing, that means what? You will have a higher chemical reactivity. For example, on the surface, atom on the surface is not well bound, right? So that means that atom on the surface will always have higher reactivity, chemical reactivity. Okay, so ladies and gentlemen, I want you to remember these important things because we are going to talk about this in chapter 4 and even chapter 5, diffusion. Okay, so this atom means that this atom is easy to react with other atoms compared to the atom compared to this atom, right? Because what? Because this atom is in the gram boundary. Okay. So let's take a look of the solidification video, and we are going to explain this. So solidification video is that looks like this. How do you make a solid from
Explain
liquid?
the solidification of metals and alloys. First, let's discuss the solidification of metals. When we pour the molten metal in the mold cavity, we see that the solidification process starts from the sides of the mold, then moves towards the molten metal. This is because the sides of the mold provide cooling to the molten metal. After some time, we see that the molten metal solidifies in the form of randomly oriented crystals. The region where the crystals are formed acts as the production area and is called the nucleus. Metal solidifies further, we see that the shape of the crystals changes to a long crystals. Having their axis perpendicular to the sides of the mold. Thus, the shape of metal crystals formed is shown. Note that during solidification of metals, the temperature is constant. This can be represented graphically as Now let's discuss the solidification of alloys. When we pour the
Okay, forget about alloy. Right, so this information tell you that when you make a solid from liquid, you want to make a very good single crystal. It's not easy from molten crystal, because when you pour the liquid of metal or molten metal in the mold, and they will start to form a small grams, and this what we call equal acid grams. Okay, so roughly the same size in all directions makes this one. So this is heat flow, and the growing direction is from outside to inside, right? From outside to inside, and heat flow is from here, because this is cool, this is hot. Okay, so equal axis is roughly same size in all directions in here. So shear of the equal axis is due to the rapid cooling. So if you have a rapid cooling, very quick, and you get the equal acid grams. And later on, you have a colonel. Colonel grams means elongated grams. Elongated grams means what? This is longer. We call it colonel. Colonel. The colonel in areas with less undercooling. So you form a gram like this. Right. So you need to know that how this formed normally. Okay. Right. The section 3.15 is anisotropic and isotropic. Anisotropic is in Mandarin, in Chinese is 意向性. In isotropic is 同向性. 意向性 means what? Anisotropic means what? You have, if you go to different direction, you have different property. So the physical properties of the single crystal of the some substance depends on the crystallographic direction in which the measurements are taken. So now let's go back to single crystal, and soon we are going to talk about polycrystal. So single crystal, you have anisotropic and isotropic. Why? In the crystal direction means what? Means linear density, right? If you have a high linear density, you have and low linear density, you will have different properties. For example, this is called anisotropic. So this is what we call directionality of the property. For example, if you have different direction in this crystal, you might have different electrical, you might have different electrical property, you might have different optical property. Okay, for 100 or 111 or planes, for example. These square brackets for direction, right? Okay. How about isotropic? Isotropic means that it doesn't matter which you perform the same properties in terms of electrical, chemical, mechanical, optical, for example, or thermal. So substances in which measured properties are independent of the directions of the measurements are isotropic. Here I give you an example. Anisotropic for the case of the single crystals. So we know this is BCC structure, like body center cubic structure. So properties are vary with directions. This is what we call anisotropic. For example, its modules of elasticity E in BCC iron. This is iron atoms, and iron is in BCC structure, is in the form of BCC structure. So, for example, this is the direction of 111. If you pull this crystal in this direction, you will have different you need to use you will measure, you will get different strengths in this direction. For example, if we take a look of this in 2 dimensions, this is what? This is this direction, right? So in this case, we can calculate the linear density. So the modules of the elasticity is about 273 gigapascal. However, if you pull this in this direction, 100, the number you get, this is 2-dimensional appearance of this direction. So you pull something like this way, right? This way or this way. You got different number. Why? It's different linear density. And in this case, you might think, well, in this case, I pull 3 atoms. In the case, just use your imagination. You pull 3 atoms and you pull 2 atoms. Of course, this number will be this difficult compared to this one. This direction, right? So the number will be higher. Something like this. But you need to measure it, and you need to calculate the linear density. So for the modules of elasticity versus the crystal orientations, for the metal, alumina, you got from 100, 111, 110, 111. You got 2 different numbers. For FCC, for BCC, you got different numbers. This is what we call anisotropy. Okay, but you can change these modules to electricity. Okay, electrical conductivity or optical properties. Okay, or the reflection index, for example, and you might get different number. So this is what we call anisotropic. So anisotropic effect versus the symmetry of the crystal structures. If the extent of the magnitude of anisotropic effect in crystalline materials are function of the symmetry of the crystal structure. So if I have 2 crystals, and one crystal has cubic structure, one crystal has triclinic structure, and I want to ask you which crystal has more and perform more anisotropic effect or perform more anisotropic properties. The answer is this one. Why? Because this is symmetry. Like if you pull in this direction, if you pull this direction, it's represent the same. However, if you think of modules of elasticity in this direction and in this direction, these 2 directions give you 2 different numbers, right? In terms of this. So this has a high anisotropic effect. Because of what? Because this is we call asymmetry. Asymmetry. ASSYMMERETRY. So we think of symmetry. This is symmetry. This is asymmetry. Okay. So if the structure tree is less, then anisotropic effect will be high. On the other hand, if you have a high asymmetry crystal structure, the anisotropic effect will be low. Okay. So in the case of the crystal structure, triclinic structure are highly anisotropic. Just now we talked about single crystal. How about polycrystalline? Polycrystalline normally, because you have many small grams get together. So crystallographic orientations of the individual grams are totally random. Of course, if you have a small, if you have hundreds of the small gram together become a polycrystalline, of course, any direction represent the same property, give you the same properties. Okay, so totally random. So grams are anisotropic for some materials, of course, but if you put grams together, so a specimen composed of the gram aggregates behaves isotropically. A single crystal, single small gram give you an isotropic property, but if you put all the grams as a whole, then this represent isotropic property. Okay. So texture, the grams in the polycrystalline materials has a preferred crystallographic orientation. This is how we want to tell you that if you have small grams, if the gram grows in the same directions, this is called you have isotropic property. But if you are elongated column, this represent isotropic property, right? Because this is long. So this direction and the property in this direction, the property in this direction will perform differently. Okay. But if you regard this as a whole, they tell you that this is non-directional. Okay. Right. So how big is it? How do you define the grams? It can be 1 nanometer or 2 centimeter. So this is what we told. This is a comparison of a single and the polycrystal for anisotropic. For example, if you have a gram like this, we already know this, so I skip this. For example, you have polycrystalline. This polycrystalline small, the gram seems all the directions. You have all the directions the same. So this is called isotropic. And if you make this elong grams, so this is anisotropic. Okay. Right. So this section is easy. So we talk about single crystal, polycrystal materials, and anisotropic and isotropic. And isotropic divided into two parts. The first part is single crystal. Second part is polycrystal. Right. So next section is very important, X-ray diffraction. How do we determine the crystal structure? If you have a material for you and I give it to you, as I talked to you in the very beginning of this chapter, I give you a very shining piece of material. It looks very nice. And what I want to ask you, it is diamond, very expensive diamond, or this is a very cheap plastic? How do you define, or how do you find out this is diamond, very expensive diamond, or very cheap plastic, piece of plastic? And X-ray diffraction, X-ray diffraction is a good tool for you to find out the answer. So the coming topic is X-ray and X-ray diffraction, which we want to determine the crystal structure of the unknown materials. But before we start to talk about X-ray first, and after X-ray, we want to understand what's X-ray diffraction. So what is X-ray? I'm sure you all understand this. Is that this is the wavelength, right? This is frequency. If you have a higher wavelength, you have low frequency. If you have a small wavelength, you have high frequency. That's what it looks like this. So the wave, it means length, right? So the unit will be length dimension will be length. Oh, okay, in this case, we use meter. So X-ray is located, the wavelength of the X-ray is located in 10 to power 10 to minus 10s, or less than 10 to minus 10s. So you know that radio wavelength, radio, microwave, infrared, visible. The visible is what? The wavelength of visible light is between what? 400 nanometer to 700 nanometers, right? And you want to use the Planck-Einstein equation to convert this wavelength to what? To the energy, okay? And after visible light, you go to ultraviolet, and after ultraviolet, you go to soft X-ray and the hard X-ray, and after that is gamma ray, which is very dangerous and is harmful for human being, right? Okay, X-ray is also harmful. So X-ray is a type of the electromagnetic radiation. So the wavelength of the X-ray is between 0.001 nanometer to 10 nanometer. So normally we think of this, we always think about use about 1 angstrom to represent X-ray. But X-ray is a huge range from 0.001 nanometer to 10 nanometer. So the energy of the X-ray is very high. If you use this equation to calculate the energy of the X-ray, for example, if you use X-ray as a wavelength of X-ray is a 1 angstrom, and you put this 1 angstrom into this equation, you will get the energy of the X-ray will be 12,400 electron volt for 1 photon, for 1 radiation. Do you have any idea what's the scale of this energy? What's the scale of this energy? This is very huge energy. So huge energy of inner shell of electrons of the elements, right? For example, if you have a lithium, okay, if you have a lithium and you want to take out electrons away from this atom, what's the energy required? If, for example, lithium has 3 electrons, and the one in the outermost shell, the energy you want to take this out, how many? What's the energy required? 5 electron volt. Okay, this is what we call first ionization. And how about the second one? 76 electron volt. How about the last one? 123 electron volt. How do you calculate this number? This you can find out by experiment. 576 you can find out by experiment. How is this number? Bohr atom model, right? Remember this number? 13.6. You need to remember this number because you have 1 electrons in the hydrogen, and take 1 electrons requires 13.6 electron volt. And lithium requires 132. And barium requires 218. Boron requires 341. Once you take out 4 electrons, you only have 1 electron left, which is represent the highest energy, right? Highest 8, 25, 38, 260, 341. This is the highest energy. It's always happen like this. The electrons in the most inner shell require highest energy. Okay, carbon is 491. Nitrogen is 668. Okay, so compared to 12,400 electrons, this is nothing. So this energy, X-ray can take out all the electrons away from this element. So this energy is very huge. That's why we use X-ray to determine something. Okay, so before we talk about this, let's think of how are we going to generate X-ray. We use gas discharge tube. I hope you still remember this is gas discharge tube. For example, this is spectrum for the hydrogen gas, right? You put hydrogen into this gas discharge tube and you apply high voltage and light come out. And you got these 4 lines in the spectrum. And you can use Ribot equation to represent these 4 energies, right? The wavelengths represent energy. So let's recall what we have learned here. In the middle of 19th century, Armstrong used this gas discharge tube to find the spectrum of the hydrogen. And after that, 1896, Zeeman, remember, he applied magnetic field and he realized this energy can split. Energy spread can split. That means the wavelengths from 1 to 2, from 1 to 3, from 1 to 5. And Stark also find out that instead of using magnetic field, if you use electrical field, the energy can also split it. I hope you still remember this. This is what we learned from quantum numbers, right? This is quantum numbers, right? And 1914, Frank Hertz, instead of using hydrogen, he put mercury into this gas discharge tube. And find out multiple electron atoms also shows the quantum behavior. We call it quantized. Energy is quantized, which is about 4.9 electron volt for 1 electron. But if we track back to the end of the 19th century, Röntgen, instead of using different material into this gas discharge tube, he put a very high voltage. It's about 35,000 volt. 35,000 volt applied into this gas discharge tube and the low pressure. If he found something strange, he found that he used the voltage. He found something strange. In the past, the light always come out. It's not special, but if he put a heavy black paper covered this gas discharge tube, he still finds something come out, which you cannot see. And if you finger your hand in front of the screen, you find your screen show you something, only show your bones in your fingers, not all the shapes in your finger. So he called this invisible light, or he called it ray. And he understands no matter what kind of cover you put, this kind of invisible light always come out. So we pass through substance. You cannot stop this ray. So he called it. So in the end, we call it ray. At that time, everybody scared. They think that your soul come out. After X-ray, your soul come out. So they call it scaring ray ghost. Right? This is ghost. Your soul come out. And nobody understand X-ray at that time. But Röntgen is a great man. He found this. And this is very useful. So, and now we understand this is electron and atom interaction. Because we put atom in this gas discharge tube, we have electron to strike the atom, and then the atom come out. This is what's going on. For example, if we put a copper as a plate here and use very high voltage, instead of changing the gas, we put copper as a target, and we use electron beam. We shoot this copper with very high electron energy. This is electron metal interaction. I hope you still remember we already talked about this topic in the chapter 2. So we put the electron, very high energetic electron, and shoot this atom. And what happened? We'll have electron cascade. The photon will come out. So this is what's going on. For example, this is one of atom. This is nucleus, and you have many electrons surrounding this nucleus. So this is the atom. And if you have an electron outside, you have an instant electron. For example, I hope you remember that instant electron will kick out electrons in this atom away, right? But if this is a high energy electron, I mean 350,000 electron volt, very high. So this electron will kick out electron in the inner shell, not outer inner shell. And what's going on? And of course, this instant electron kick out one of the electron in the inner shell away, what we call secondary electron. Secondary electron means what? The electron from the atom. And of course, this instant electron won't stay here. It will come out. We call it scattered electron. Of course, this high energy, this will be low energy. You might ask me, Professor, is it possible to kick out electron with low energy from outer shell? It is possible, but now we are talking about the case of the X-ray. So we assume that this very high energy, so you can take out electron from the inner shell, secondary electron and scattered electron. And what happens? There's a space here. There's a vacancy to fill the electron, right? So the electron in the outer shell will cascade from outer shell to the inner shell. And what happens? Energy exchange. This energy will exchange to what? Electromagnetic radiation. Okay, we call X-ray. It can be from outer, you will be visible light, but inner, the energy is high, so we call it X-ray. Okay, this is how are we going to generate X-ray? So, for example, the copper 1s is 1s, right? This is 1s. The atom in a 1s orbital. And if you use that, if you take out all these elements, all the electrons from out, and you use the Bohr model to calculate the energy, this energy only 11.4 Kelvin, K electron volt, which is much less than the energy of the X-ray. So this can definitely take out, X-ray can definitely take out the electrons from the inner shell, right? Okay, so this is what we understand is that if we have instant energy, which the kinetic energy is about 0.5 times mass times the velocity power 2, this is the energy. And then have energy exchange from this energy to this energy, right? Okay, so if the electron cascade from N2 to the N1, we call it alpha. If any electron cascade from N2, N3, N4, N5 cascade to the N1, this is what we call K here. K alpha, K beta, K gamma. If the electron cascade from the third layer to the second layer, we use L as a symbol. We call L alpha, L beta, L gamma. So this is what we learned. So we have electromagnetic emission like this. So N equal to 1. If the cascade to 1, that will be K alpha, beta, K gamma, K delta. Okay? And then if N cascade to 2, that will be K alpha, K beta, K gamma, blah, blah, blah. But as you know, what we want to understand is this is important because from this one, K alpha and K delta will be very close because this energy gap is very, very small already. From N equal to 3, 4, 5, it's very, very small. So what you care is this energy is this energy from alpha, beta, gamma most. Okay? So I hope you still remember Rydberg equation. Rydberg equation tell you that this is Riemann series, this is Balmer series, this is Paschen series. Okay? The energy cascade to the n equal to 1 is called Balmer series. And cascade to n equal to 1 is Riemann series. So we can use Rydberg equation to represent single electrons, followed by Bohr atomic model, right? So we understand this is the equation. We can do the calculation, and we can predict the energy of this all the cascade, or of this all the energies. So can we use the same method to calculate? Can we have an equation to calculate this energy or not? Because this is multi-electrons. This is not Bohr atomic model. Can we? Yes, we can. We have a modified equation to tell you this. So the energy diagram of hydrogen looks like this. And how about the copper? If we have a copper 90, which has 29 electrons, this has only one electron, right? The copper 29 electrons. So we have K alpha 1, K beta, if we have n equal to 2, that will be 2s, 2p, and 2p has 3 energy gap, right? Has 3 energy level. Have 3 energy states. Okay, so this is alpha 1, K alpha 2. And then go to the K beta, right? Because n equal to 3, there will be n1, n2, and n2, 3, and n2, 4, 5, n4, 5, something like that. Right, so for K alpha, 1 will be, the energy will be 8,048.1 electron volt. We use K alpha 1 can also represent KL3. KL3 means what? This is L3. The energy from KL3 dropped to the K1, what we call KL3. So K alpha 1 will be this energy. And if you use Planck-Einstein equation, you can calculate this energy to wavelength, which is this one, lambda equal to 1.540 angstrom. When you go to the graduate school and use X-ray, you need to know this number. Why? Because now the X-ray all come from copper. So this is the X-ray you want. This is the wavelength. And this 1.540 angstrom is from copper K alpha 1. Copper K alpha 1, which is 1.540 angstrom. When you go to health check, or when you have you have teeth problem, you go to dentist, you have X-ray. It's all X-ray using the source of copper. Okay, and then the energy of the K alpha 2 will be this number. We also use the KL2 to represent. Okay, and KL1, something like this. And you can have K beta, K gamma, K delta. So this is what we call characteristic X-ray. So when the X-ray comes from this number, if I told you that the wavelength of the 1.5 angstrom and in the K alpha 1, what is this material? You will quickly say, oh, this is copper. So if you put an unknown target in the X-ray discharge tube, and then you come out with spectrums, with the energies, and you realize these energies belong to you realize what is this material. So this is what we call characteristic X-ray. So the characteristic X-ray copper has its own X-ray come out. So by the detection of X-ray, you know what is this material. You put silver, and silver give you different X-ray. You put copper, you put gold, they all give you a different X-ray. They all give you the X-ray with different wavelengths, I should say in this way. Okay, so think of KLM N shell. right? And here electron configuration, this is the second quantum number, right? 1s, 2s, 2p, 3s, 3p, 3d, 4. And this is the fourth quantum, this is the third quantum number. Sorry, this, okay? Right, so X-ray emission line, C-bond notation, you have two different notation. One is called C-bond notation, one is called IUPAC notation. IUPAC is more official, but C-bond is, when you, the people who start to, the person or people start to find out this, they define and they use their name, C-bond. So this is how it looks like for the copper. The KL1 will be 7,884, and the wavelength will be 1.57244. The KL2 1.54432, something like this. So this is, this is the characteristic X-ray wavelength of the copper. So when you put an unknown material, metals, into the X-ray, and a series of X-ray will come out, and you can identify what kind of material or what kind of metal you examine. Okay. So as I told you that there are some important X-rays. That's why we call characteristic X-ray. So if you put copper into the gas discharge tube, you come out with X-ray, and you plot the wavelength in x-axis and intensity in y-axis. You'll find out peak like this, K alpha, K beta. The wavelengths represent energy. So you have one energy here and energy intensity here, K alpha 1, K beta, and a K alpha 2. So this is the wavelength. And K alpha is about 1.54, and K beta is about 1.39. How about L energy? L energy will be weaker, right? This is stronger, this is weaker, because L here, right? K here, L here. So weaker one, you got something like this. So this is what characteristic X-ray of copper. And for silver, you got different, you got location of the K alpha, K beta, and K gamma. It might be here. It might be here. L region also different. So you can identify the materials according to this figure, because it shows you always different for the copper, for the silver, for the gold, for the platinum. Okay? So this is called characteristic X-ray of the copper. So as I told you, that you can put different metals in anode here, and you got different spectrum. So this is what we call mostly steps later. This looks like later, right? And mostly low. This one line represent the wavelength. The wavelength represent energy. Again, can you use an equation to represent these energies, or predict the energies by equation? So for example, this is calcium, titanium, vanadium, okay, chromium, manganese, okay. So you got letters here. If you put different metals in the anode, you got it. Okay, and mostly found this. So that's why we call mostly steps data. So mostly law is an empirical law concerning the characteristic X-rays that are emitted by atoms, different elements. So you mostly want to use an equation to represent these energies. Can he do that? Yes, he can. He modified the equation. Okay, this is empirical means what? Empirical means that you don't get this equation by calculation, by theoretical calculation. You use experiment and use some parameters to fit the answer. That's why we call it empirical. Empirical. So Moseley law looks like this. He mostly the Rieber equation by using a parameter here. Okay, this R represents the same. Okay, so as we know, the wavelength is the reciprocal of wave function. And then for this symbol, the delta sigma. For the sigma, this one is called screen factor. For the K alpha 1, you use 1 here. For K beta, you use 7.4 here. Why 7.4? You know, the screen factor tell you that if K beta means that you probably 8 electrons outside, but you want this screen factor, you want to take out the one in the bottom in the most inner shell. So that's why you have 7 electrons outside. But you know, if you do that, you will put 7 or 8, it doesn't fit this equation. So in the end, he used 7.4. So this 7.4 means you put 7.4 here. Okay, so this is some of the simple calculation for K shell to L shell to K shell. That means the 2 to 1, and this is how it looks like. And from M to K, you use this equation. Use 7.4 is the 1. Okay. I don't need you to remember this equation. You just need to know Moseley law is a modified equation from the Rieber equation. Okay, is it interesting? Right. So very quick. So you know, as I told you that the characteristic X-ray is for the metals you want to know. So we put different metals into the gas discharge tube, for example, copper, moly, and tungsten. And the K alpha 1 for 1.54 Armstrong. K alpha 1 for the moly is 0.709 Armstrong. The K alpha 1 for tungsten is 0.207 Armstrong. So as you know, the wavelength, as you know, the atoms, the electrons in the element is increasing. That means it's more difficult, right? It's more difficult because you have more proton and neutron in the center. So if you want to take out the inner electron from the inner shell, it requires higher energy. If you require higher energy, the wavelength will be smaller and represent higher energy. So as you can see, the number is different, and the wavelength decrease. And this represents tungsten. This represents moly. This represents copper. Although they are all from K alpha 1 shell, the wavelength is all in K alpha 1 region. So all the numbers you can find out in X-ray transition energy and database. Okay. So this is the characteristic X-ray of energy and the elements. So please, it's easy in the old time you find this. So this is how characteristic X-ray. Please read this by yourself. Right. Okay. So that's it. I think we have talked, but we run out of our time today. We will continue the X-ray information or X-ray lecture on Friday. Okay.